We're very honored to have Alex Pham joining us from Toyota. He builds everything. So if you love Toyota, that's all Alex. If you don't like Toyota, then it's all me. But we're very honored to have him here. And Alex is going to be sharing some actual data from testing that they've done inside their vehicles in the AI space. That's the topic that we're going to be tackling today. We're going to be tackling about how do we get from today to tomorrow with AI at the edge. By the way, how many people here have heard of AI? No one. Oh, well, let me educate you. No. So AI, it's got to be the hottest topic out there, right? I mean, that's what everybody's talking about. We certainly have a long history with having more and more compute going on at the edge. As we talk about where we've come from, we used to have AI and the edge, right? Where we had some smarts, some dumbs, running inside cars and vehicles as they're traveling around. But the idea was that they were sending data back to the mothership, where you had some sort of AI model that was taking this information in, doing later training, doing fine tuning. And that kind of is a yesterday approach to things. Today, we're faced with a different problem. In the past, we focused primarily on securing the edge, the cost of the edge, and networking, especially bandwidth and latency. That hasn't gone away. That's still a problem. But today, we're starting to see the moving of computation and inference moving out to the edge. So now we're talking about AI at the edge, as distinct from AI and the edge. Now, this presents a number of different challenges. If we take a look at AI being the inference happening at the edge, and instead of just passing the data back to the mothership, we're actually consuming it on board. This provides some computational challenges. Also, the models that are being used, we can't just take, GPT-4o and put it on a, in a vehicle. That's just not going to work. We can't line up a whole bunch of GPUs inside the dashboard. That just isn't going to work. So we have some significant challenges. We're going to be diving into those. And as we look ahead into tomorrow, let's assume we've solved all those challenges. We're going to have huge challenges as the edge talks to the edge. So we're talking about AI across the edge. When we get to that point, we're going to have massive governance problems, orchestration problems, and sovereignty. Who actually owns the data? Maybe more correctly for a vehicle, who actually gets the traffic ticket? Is it Toyota? Is it the AI company? Or is it Alex because he just can't slow down, right? This is going to be a big challenge, especially for Alex. So when we take a look at this, we're talking about a series of generations of AI working with the edge, at the edge, and across the edge. And to get from today to tomorrow, the focus of our talk, we're talking about how do we solve today's challenges so that we can begin to start tackling tomorrow's. Okay, let's look at those three challenges. We're going to dive into compute first. When we talk about better edge compute specifically, we're talking about faster inference and less power consumption. Right? Probably not a shock to anyone here, but these are the two biggest problems facing AI at the edge today. If we look at a continuum of compute devices, starting from the core, so public cloud, inside the data center, inside your colo, we have spent generations working with CPUs. We've seen the advent of GPUs and a lot of AI workload offloaded to them. Neither of these two are very scalable or very economic to do at the edge. And so we've seen several new advents coming on, most recently with custom ASICs. That's been around for a bit. But we're also seeing photonics. That's a little bit more forward-looking. And even further looking, there are analog compute devices that, at least in the early prototypes, are showing 3 orders of magnitude more efficiency of dealing with vector mathematics, or AI inference, if you will, at the edge. So look for more of those to be coming. So these are some of the answers to the challenges with getting better compute at the end. we're going to talk about a real example here. So Alex is going to talk about what is actually going on at Toyota. So other than just PowerPoint slides, what are some real numbers? What are some real experiments and real results we can share? Alex, go ahead.
At Toyota, we do some evaluation. As Mark just mentioned, you have both from the core to the edge. So we implement as we look at the platform where we are used for the A140 megabyte, the A180 megabyte, and then the RTX, which is the 3090. You all know that already. Then we also go down to the edge level, which is we look at the Jetson Nano, the Raspberry Pi, and then the Snapdragon. The criteria that we use in the evaluation of this, as in any company, you probably use something different. For us, what we care about is 6 things. First of all, the number of the parameters, what are the teraflop look like, what are the memory usage, the prediction error, which is an accuracy rate, your power consumption, and the test time. So, next. So, I will start with the cloud. Now, if you look at these things I want to mention first, the closer to the center, the better. So, in fact, we look at the 4 different types of AI model and what we want to deploy at the cloud. One of them, the first one is called the Neuro ODE, which stands for Neuro Ordinary Differential Equation, and the RNN, which is probably most of you know, and then the NNN, and we develop our own model. In this context, we look at all the parameters, which I just mentioned, which is how many parameters there are, the powers, the error, the memory, the teraflop, and the test time. And you can see the variety of different models and how they affect the compute or affect this type of parameters. So for example, RNN use a fairly high memory and use quite a bit of parameter versus like the neural model, they actually use a lot less memory, but the test time is long and the power consumption is high. So we want to look for the model of what we develop, and we look at one thing here of what we want to look for is the error rate. The lower the error rate, the better. So therefore, what we did on this one is the lowest error rate. So the green area is what we look for, and this is where we believe that given our model is probably have a fairly good power consumption in this context under the A140 40 megabyte and the A180 megabyte. Now, assuming that you have 2 of the same, one single model, and you run this on the same 2 different hardware platforms, one of them is 30% cost better than the other one, then why would you pay more? So I was able to use this with this configuration. So that's the drive insight of what we got for this. Let's move to the edge. Okay? Now, we conduct a similar experiment leveraging and using the edge in this context. Again, you look at the Pham model and how they deploy at the edge, because what you want is not only have the core model running in the cloud, but as an edge device itself. In this context, we look at all the permutation and the parameters again. The context in this one is power. Because power is what we care most in the limited resources within the edge device, specifically within the vehicle. And then the accuracy, how much that and how much memory is used. So our conclusion is, actually, if you look at this model, the Dragon is actually pretty good on the test time. The Nano also test time, but the power consumption is actually very good on the Raspberry Pi. So when you look at specifically AI model and targeted your edge deployment, see how they all fit, and all these parameters are other parameters what you care about in your own organization. Some people more about security, storage, data, and so forth.
All right. So here are the conclusions and a summary of what Alex just explained, where we see various different test results on different platforms. Obviously, this is a sampling of platforms. There are actually more than 3 manufacturers out there. But these are the results in summary.
Yes.
All right.
We test quite a bit, extensively, a number of different platforms, but I thought 3 is enough for people to take a look at.
Let's talk about another challenge we're facing right now. We're talking about not just bandwidth and latency in the network, but actually the connectivity and coverage. And the term we're using for that is the mesh. We need a better edge mesh. So when we talk about that, the biggest points of measurement there are how much control does a company like Toyota get over the connectivity, the bandwidth, the specific protocols, and how much coverage. Does it work in the middle of Texas? Does it work in downtown New York? So when we take a look at that, for years we've been dealing with public wireless and wired communications. Primarily right now we're talking about 5G, but as we move into the future, we're starting to see more and more private 5G. In fact, there's a number of booths and probably some of you sitting here right now that actually work in this space, where we're talking about moving from the public 5G to private 5G, but also moving from WAN into SD-WAN. The new movement is, of course, using non-terrestrial networking, and that's both low Earth orbit, high Earth orbit, technologies out there. You'll recognize a number of the logos on there. So by the way, congratulations to anyone here from SpaceX. The headline read, SpaceX launches booster without exploding. I'm thinking if your headline has to have the words without exploding, that kind of says that you're a little bit earlier in your phase, but nonetheless. So as we talk about more coverage, obviously the satellite space is what we're talking about. Alex has got a use case here to talk about the autonomous vehicle mesh.
Actually, it's classified, so I could not talk a whole lot about it. But what I can share with you is this. Imagine, now, what happened is, if you had a very cohesive, integrated network across your private 5G, across your vehicle, across the cloud, how did that deliver the infotainment experience? How did that deliver the mobility experience? And that's exactly what we're after. If you want to hear more about us, come next year.
There's your teaser. There's your teaser. It's like Game of Thrones in here, right? Okay.
But
so,
I can give you a little bit tidbit. We work with one company there that's Monogoto. That's one of the one that we can do a little bit of testing with.
and they have a booth, I think, just right over this direction. Anyway, we'll talk about, we do need better edge models. And specifically, what do we mean by better in this case? We mean a smaller footprint and more inference efficiency. When we take a look at this space, we certainly have small language models. You'll recognize some of the logos in there. This is probably the fastest growing area of AI right now, is the reduction of parameter size in small language models. But we're also seeing inference acceleration. Now, this has been around for a while, primarily pointed at the core, at cloud and data center-based workloads. But the idea here is, can we optimize and accelerate the actual AI network itself? Can we do precision reduction? Can we prune out unused or low usage areas of the network so that that footprint can be reduced and thereby increasing inference? We also are talking about federated models. Alex is going to talk about an example here, but the idea being, what if the small language models weren't operating independently? What if they could all assist and collaborate in a confederated mesh, calling back to our previous slides? What if that was the plan? And that is definitely the way things are going. So, when we talk about small language models, for those who aren't aware, we say small compared to large, right? So when we talk about the number of parameters in a small language model, we're still talking in the billions, but we're talking in the 2 billion, 3 billion, maybe up to 13 billion parameters. When I first started working in AI, that was under the first Bush administration. That shows how old I am, right? We measured things in the dozens of parameters. So talking about billions of parameters as being small, I mean, this has come quite a ways. If we take a comparison of those exact models that we just had and compared it against, say, like GPT-4, or even Google's Gemini, you can see that we are talking orders of magnitude smaller. So when compared to these blue whales of models that are out there, we're dealing with mere goldfish here, right? And that's exactly what we're looking for inside of a vehicle. We're looking for that smaller footprint, not just to reduce memory consumption, which is certainly true, but also to reduce power consumption and also speed up inference times. So we're talking about hundreds of times smaller than the large models that are out there. And by the way, the large models continue to grow. The small models continue to shrink. So a couple years from now, this model is going to be even more exaggerated, but that is certainly the way things are going. Okay, Alex, this is your use case.
Okay, let's talk about the real AI edge use case of what we have. First of all, who know about BEV? Very right. One of the area of BEV, definitely the two things that most concern people about. First of all, is how long is the range, which is how far and how fast and what's the distance of the BEV can provide. Secondly, is what is my battery life going to look like? So what we did is, okay, so I'll go in this context. We use and build the model to validate the battery life estimation and the range estimation. Now, we use a little bit different criteria than what we did before. In this use cases, what we did is we did test for the last time, which is the accuracy, the training bandwidth, and then the compute. And we use three different type of category. The first one is the centralized learning, which we all know as a yesterday model that Mark just talked about before, where all the data go to the cloud, and then the federated model where we use the vehicle, and then finally we put in the personalization for federated learning. So, Mark, next. Now, this one as a centralized learning model, which we know exists today, we have take all the data from the vehicle or at your edge device, and we send it out to the cloud. The cloud crunch everything associated with this type of architecture pattern. Second. Okay, in the federated model, you actually have the model reside within the vehicle. Some of them are shared among the vehicle, within the vehicle, and aggregated as in the cloud, and send the data back or send the knowledge back to the vehicle. Third, finally, we not only put on that, but we put in the personal touch of or your personalization. The way that you drive is a little bit different. The area that you drive is a little bit different. So it's the eastern side and then the western side in the desert and a different type of condition. So it's personalized to where you're at and personalized on your driving behavior and your personal vehicle as well. And what we determine is, okay, now, if you look at the central model here, the accuracy is pretty good, but you do the average, it's lower. But now you put in the personalization, you have a better experience and better accuracy overall. You look at the training time, and this is fairly significant in the cloud. When you do a federated learning, both federated learning and the personalized, actually you save quite a bit. Finally, the bandwidth, which is key. And this is where edge computing makes a significant difference, because if I have to transfer this much data to the cloud, versus actually I can transfer only this much to the cloud. That communication cost is huge. And finally, the compute, as you can see in the central cloud, versus actually can you derive at the edge as well. So at the end of our conclusion is what we can see. For the accuracy, we have 20% better accuracy than what we with the central cloud model. Training time is about 50% faster, a lot less bandwidth on the communication, specifically on your vehicle, and finally 23% compute faster.
That's certainly impressive. That certainly is impressive. So we talked about the challenges we have today. The challenges we're going to be facing tomorrow. Alex, do you want to expand upon some of these?
Yes, just a little bit. Let me touch on it. So, sovereignty. Imagine you drive a car, and in this case, it's you in Europe. You drive from one country, it have privacy, security associated with your car. You cross the country on the other side, they have the different privacy. You can no longer get all the data of what you need in the vehicle. What are you going to do? You have to delete all of them. So sovereignty is something that we have to experience. Now, imagine in the next few years, what are the tools that I have allow me on your vehicle that we to manage your data privacy. When you want to delete it, we delete it. If you cross somewhere that's not in the different law, we capture a different type of activity. This is where we are going with such a tool to understand the sovereignty. Next thing is orchestration. Orchestration is basically how do we handle hundreds and millions of type of equipment. Specifically, the model of what we're looking at is not only managing the number of edge device, but the AI application and your edge application associated with this as well. Finally, you have to govern all this information across all the different edge device, which is a lot of complexity than current in the cloud as of today.
So next year when you come here, Alex is going to have answers to all of these. He will have fixed them all by then.
Not by all, but I can give you some more info, more ideas by that point.
So our takeaways here of where we've come from and the challenges of yesterday are still with us today. The challenges that companies like Toyota are facing today, the biggest hurdles they've got, and where we're going to be heading, right? There's more challenges ahead for us. All right. We'd like to open it up to Q&A here. There must be a ton of questions out there.
Yep. Happy to help with the mic. Any questions in the room?
Well, I'll tell you what, I'll throw you guys a question then. So do you think this only applies to BEVs and autonomous vehicles and hybrid vehicles? Is that the only area this applies? What do you think, Alex?
It's apply a lot more, but I would like you to take the key away, at least from this presentation. First of all, what you've learned a little bit today is that edge computing is real. We find significant value compared with cloud computing in that, so it's going to stay. As AI is here to stay, we proved that with the federated learning model. And not only that, you look at the small language model, what will come next as a small language model of what Mark mentioned. So imagine you're in the vehicle, you interact with the vehicle. How do you connect all this back to the cloud and get the data transferred back and then give you an answer? Well, large language model will have that latency and performance is really long, but I can train that small model. For example, you ask, oh, how do I turn on my windshield? It doesn't need to go to the cloud. It's practically in the vehicle. And that's where the small language model will help. So as it is, the edge AI application is real. So edge computing here to stay.
There we go. That means we've got a spot next year. So anyway, I thank you all for spending time with us. It's been an enjoyable experience. Thank you much.
Thank you. Woo!